coordinate system, slope, area, length. Rectangular, parametric, polar. Rectangular example with line. Rectangular functions use the x inputs that varies from a to b to get the y outputs using f of x equals y. Parametric example with asteroid. Parametric equations use the input parameter t that varies from a to b to get x and y outputs using f of t equals x and g of t equals y. A parametric curve has direction since it goes from its initial point to its terminal point. X equals cosine t cubed and y equals sine t cubed with t greater than or equal to 0, less than or equal to 2 pi. Polar example with cardioid. The polar coordinates of a point P is r of theta, theta, where r is the distance between the origin O and P, and theta is the counterclockwise angle between the polar axis, which lies on the positive x-axis, and the line OP. Negative radius means going in the direction of that angle, but backwards. Note that r squared equals x squared plus y squared, and tangent theta equals y over x. R of theta equals 1 plus sine of theta, with theta greater than or equal to 0, less than or equal to 2 pi. Slope, parametric. To find the slope for parametric, we start with the slope for rectangular, dy dx, and use chain rule. Note that x equals f of t and y equals g of t. To find the second derivative, replace y with dy dx in the formula. Let's find the slope of the asteroid, x equals cosine t cubed and y equals sine t cubed. Dy dx ultimately equals minus tangent of t. Slope, polar. To find the slope for polar, we adapt the parametric slope by replacing t with theta. Note that x of theta equals r of theta cosine theta, and y of theta equals r of theta sine of theta need product rule. Dy dx equals the following. Let's find the slope of the cardioid, r of theta equals 1 plus sine of theta. In practice questions, we will probably evaluate this for a certain angle. Dy dx equals the following. Area, polar. To remember the area formula for polar, consider a circle's area in relation to how much angle we've traveled. Area, angle. Pi r squared, 2 pi. R squared over 2, 1. Half r squared theta, theta. Eventually, we'll get integral from a to b half r squared d theta. Be careful if finding the area between two polar functions, because it's not simply subtracting the larger function f and the smaller function g. Area inside larger function f minus area outside smaller function g. And we get the following. For questions, find the angles for the intersection points and use those as the limits of integration. In practice questions, there can be multiple equivalent setups of the integrals due to symmetry. Let's find the area enclosed by the cardioid r of theta equals 1 plus sine of theta, with theta greater than or equal to 0, less than or equal to 2 pi. We have the following. In practice questions, we might use identities like the following. Here are the calculations. By the way, calculations could have been simpler if we had noted that the integrals for the second and third addends are 0 since they're over full periods. Length, rectangular and parametric. The formulas for length are based upon the Pythagorean theorem. The parametric formula comes from substituting dy dx equals this and dx equaling this. Let's find the perimeter of the asteroid x equals cosine t cubed and y equals sine t cubed, with t greater than or equal to 0, less than or equal to 2 pi. Start with 4 times the length in the first quadrant, and we get the following. Continuing. With simplification, since sine of t and cosine t are positive for t greater than or equal to 0, less than or equal to pi over 2, we get the following. Parametric movement. The parametric first and second derivatives can be applied to position, velocity, acceleration questions. And we have the following. Note that speed is the absolute value of velocity, that is, the length of the velocity vector. And we have the following.